In today's lecture, we are going to discuss about oxides of group 4 elements and IC fabrication. So let's start first with the oxides of group 4 elements. In group 4, we have carbon, silicon, germanium, tin and lead. So here we have carbon in the first atom and its oxides are carbon monoxide, carbon dioxide. So these oxides present in the top of the table are acidic in nature, which means the elements which are present at the top of the group carbon, silicon, they have oxides which are acidic in nature, and the group's elements present at the bottom of the group germanium, tin, lead have oxides which are more basic in nature. The acidic nature of the oxides decreases down the group. So when we go from carbon to lead, the acidic nature of the corresponding oxides or go down the group from carbon to lead, the oxides of the corresponding elements decrease in their acidic nature, and the elements at the bottom have basic nature. So their oxides are basic and the oxides of the top elements are acidic. So these elements, when we go down, the acidic nature only decreases but it will not disappear, which means the oxides of germanium, tin and lead will also possess acidic character, but their basic nature is comparatively more, which means the oxides of these atoms possess both acidic and basic character. So the compounds which possess both acidic and basic character are called amphoteric. So the oxides of the elements present in the group 4 which are at the bottom of the table are amphoteric in nature, and the oxides of carbon and silicon which are present at the top of the table have acidic in nature. So the carbon oxides which are carbon monoxide and carbon dioxide. So carbon dioxide is highly acidic, but the carbon monoxide is neutral. So the oxides of carbon which are carbon dioxide and carbon monoxide, this one is acidic and the CO is neutral. And the next element SiO2, which is the oxide of silicon, is also acidic in nature. So what happens here is we are morely interested in silicon and germanium as they are the semiconductor materials. So we are focused on the silicon and germanium elements of the group. So the silicon oxide, which is SiO2, is acidic in nature and it reacts with a base NaOH to give Na2SiO3 plus H2O. So this is water and this is sodium salt of silicate, and this is SiO2 which is acidic in nature and it reacts with the base. So the acid reacts with the base to give a salt, and the water is called neutralization reaction. So when we look at this equation, you have two sodium elements here and then only one sodium here. So you need to put a 2 here so that we will try to fix this equation. So silicon is 1, oxygen is 4, oxygen is 3 plus 1, 4, and then 2 sodium and 2 sodium and 2 hydrogen, 2 hydrogen. So this equation is balanced. So when we look at the next element, germanium, its oxide is germanium oxide. This is amphoteric in nature. So amphoteric means it can react with both acid and a base. So when we put an acid HCl, it gives GeCl2 plus H2O. So what happens here is it forms a salt with the acid, and then water is produced, which is neutralization reaction. So here you have germanium oxide, which acts as a base here, so that it reacts with the acid to give the salt. You have two chloride here and you have only one here, so you need to put two here. So if I put 2, the hydrogen count is 2, which is equal to the product in the, water has 2 hydrogen, so that's why hydrogen is balanced, and germanium is 1 here, so it is also balanced. So this is a balanced reaction, and this reaction tells GeO, which is germanium oxide, acts as a base which reacts with the acid to give a salt of germanium and then water. So now if it acts as a acid, it should react with a base to give again a germanium salt, which is sodium salt of germanium oxide plus water. So here germanium oxide plus a base, actually this acts as an acid, so it reacts with the base, so that to give a salt and water. And if we try to balance this equation, again we need to put a 2 here, so that you have 2 sodium here and 2 sodium here. So this is the reactions which tells sulfur dioxide, which acts as an acid, can react with the base, so that it forms a salt, and then germanium oxide, which can act as both as an acid and base, so that when it acts as a base, it reacts with acid to give a salt, and then when it acts as an acid, it can react with the base to give another salt. So this is amphoteric, which can act as both as an acid as well as a base. So the elements present at the bottom of the table can act as amphoteric oxides, so that they are basic as well as acidic in nature. Next we will look at the specific oxide of silicon, which is interestingly used in the electronic industries. SiO2 is the oxide of silicon which is present in the group, and first we start with the preparation. So in preparation we use thermal oxidation method. So in thermal oxidation method, what we do is you heat silicon to a high temperature, and then it will produce SiO2. So the temperature usually used here is around 900 to 1200 degree centigrade. So silicon is taken and then it is given silicon dioxide in the presence of heat and oxygen. This can be done in two methods. The first method is wet thermal oxidation method. So in wet thermal oxidation method, we use water and silicon. So silicon plus water at high temperature gives SiO2 plus hydrogen. So here you have 2 hydrogen and you have 2 hydrogen here, and oxygen is 2 here, so it is only 1 here. In order to balance, we need to put a 2 here, which makes the hydrogen count 4, so it needs to be 2 here. Now the equation is balanced. So in wet thermal oxidation, we have silicon reacting with water in the presence of high temperature, usually around 900 to 1200 degree centigrade. It produces silicon dioxide. So silicon dioxide is produced along with the evolution of hydrogen gas. In the next step, you can perform, instead of wet, you can make it dry thermal oxidation. So the name dry indicates that we are not using any water here. Instead, we use oxygen gas. So you have silicon here, it is combined with oxygen at high temperature to give SiO2. So here you have silicon, oxygen without any water. That's why it is called as dry thermal oxidation, and it produces SiO2. In this way, silicon dioxide can be produced in the laboratories. So silicon dioxide can be produced by several methods. We have discussed only about thermal oxidation method. In thermal oxidation method, we have wet thermal oxidation and dry thermal oxidation. That's what we discussed up to now. Next, we will look at the properties of silicon dioxide and why it is used in silicon-based industries. Properties. So the main property of silicon dioxide is, the first one is the dielectric nature. So it is used as a dielectric material in silicon based industries because it has a wide band gap, which means the gap between the valence band and the conduction band, valence band and conduction band, has a huge energy difference that makes it to be used as a dielectric material in electronic industries. The second one is it is a good corrosion resistance material, which means it will not be corroded and it can act as a fine thin layer on surfaces to protect other materials. And then the other important properties include optical transparency, which means the compound can, silicon dioxide can permit any radiations to pass through it. It looks very transparent to the surface where it is coated. And then next, it is resistant to chemicals. Resistant to chemical means it can be coated on any material so that that material can be protected from chemical attacks. So this is used mainly in IC fabrication etching process. In etching process, you use chemicals to dissolve the material. At that place, you have silicon dioxide, which is chemically resistant, will protect the silicon wafer. The final property which is very important in the case of silicon dioxide is high temperature withstanding property. It can withstand very high temperature so that it can be used in fine lining in the furnaces. Next, we look at few applications of silicon dioxide. Applications, first we will discuss about the packaging industries. Packaging means it is mainly food packaging. So in food packing industries, you use PP, which is isotactic polypropylene, and then PET. PET is polyethylene terephthalate. Polyethylene terephthalate. So these two polymers are used in food packaging industries. So when you pack food, it will be covered with these polymers, but these polymers are contain pores on the surface. So these pores will allow gases to pass through the polymer material, which will make that material not sufficient for the property what it is designed, which means when the gas enters the package, it will create spoilage of food. As a result, it will not serve its purpose. So in such industries, what they do is they coat silicon dioxide on this polymer material. As a result, the polymer material can protect the penetrating gases to the food material. So these silicon dioxides can be used in packaging industries in order to prevent the yearly spoilage of food. The second property is corrosion resistance. Corrosion resistance property of corrosion resistance property. So because of its corrosion resistance, this SiO2 can be coated on a metal surface or any material which needs to be protected from corrosion. Thirdly, it is used in solar cells. So in solar cells, their role is it is coated on the material which converts the solar energy into electrical energy. Since it is optically transparent, it allows the light to pass through the material, and this will act as it can absorb more and more light energy to the surface of the material. And then the second purpose in solar cell is about its dielectric nature, because the band gap of silicon dioxide is 8 times that of silicon, which means SiO2, when we are coating on the surface, it acts as a good insulator so that it will not conduct, and it differs from the pure silicon crystals. With this, we end the concept of oxides of group 4 elements. The next heading is fabrication of IC, which means fabrication of integrated circuits. So integrated circuits are otherwise called as chips or microchips. So these chips and microchips are manufactured in industries based on the requirement of the customers. So integrated circuit or the chips are the basic component of all electronic items such as camera or any ID card or whatever the things we use, like your mobile phone sims. So everything has a chip which will read the signal and it will pass through the circuit. Next, we will look at the production of IC fabrication. So IC fabrication involves five independent steps which can be used to manufacture the chips. So in the chips, you start with the uh, pure crystalline silica, and from pure crystalline silica, each step needs to be done to make it as a usable chip. The first step in this process is wafer production, and the second important step is masking or photolithography, and the third step is etching, fourth step is doping, and the final important step is metallization. So in today's class we will discuss about wafer production, which is the first step of IC fabrication. So in IC fabrication, the first step is production of wafers. So you imagine there is a furnace. In the furnace, you kept pure silicon. So this is the furnace, and in the furnace you have the heating element which we call heater, and inside you have the molten pure silicon. The inner coating of this furnace is done with the help of silicon dioxide. As we discussed, silicon dioxide can act as a very high temperature withstanding material. That's why it can be used for lining in the heater. So you have molten silica here, and then the heater which will provide heat in order to melt this silicon material. This is covered with the thermal shield. So this part is called thermal shield, which will protect the heat from losing. So the pure crystalline silica is heated here to very high temperature, and then it is inserted with pure single crystalline silica. Pure single crystalline silica. So this pure crystalline silicon is dipped into this solution and it is pulled out of this solution. As a result, you will get ingot. So this ingot looks something like this. So this is ingot which is produced from this molten silica on dipping pure crystalline silica. So this comes out as a cooled material and this looks like this. So what we do is we use a diamond tipped saw to cut this into small slices. So the slices will come out like this. So these slices are called silicon wafers. Silicon wafers. So what we done up to now is you take silicon dioxide from the sand, and the silicon dioxide you take out only the pure crystalline silica, and then pure crystalline silicon is molted in this heated bath. So the thermal shield will protect the heat lossage from this process, and the lining inside here is made up of SiO2. I haven't written it here. So SiO2 lining is done in order to withstand very high temperature. So this molten silicon is cooled down and then it is inserted with a pure crystalline silica to produce ingot. So this ingot then it is sliced down into pieces by this diamond tipped saw, which means this will slice small pieces of the ingot into a circular silicon wafer. So the silicon wafers is somewhat circle in shape, and then this is what we start the IC fabrication process. So from this silicon wafers you can put the transistors, resistors on top of it, and then you will complete it as a chip. So the thickness of the silicon wafer produced here, the thickness is equal to 0.01 to 0.025 inches. So this is the thickness of the material what we produced here. The silicon wafers produced here are of thickness 0.01 to 0.025 inches. So these silicon wafers are cut used this diamond tipped saw. As a result, the edges of this thing are very rough in nature. So at the end you need to smoothen it by polishing. Next you need to clean and dry that silicon. Now we discussed about IC fabrication technique. In the technique you use the first method, production of silicon wafer. So that is the one we discussed in this class. In the next class we will discuss about the other 4 steps involved in this process. Thank you.